On August 8, 1944, at 14:30 hours, Oberstleutnant Hans von Luck stood in the commander's cupola of his Panther AUSFG, watching through his binoculars as American Sherman tanks crested the hill 3 kilometers south of Mortain. He counted carefully. 12 Shermans, then 20, then 35. He stopped counting at 50. More were still coming. Von Luck commanded the 125th Panzer Grenadier Regiment. His battalion had 6 operational Panthers, 2 of Germany's finest tanks. Each Panther mounted a 75mm high-velocity gun that could penetrate a Sherman's frontal armor at 2,000 meters. The Sherman's 75mm gun could only penetrate a Panther's frontal armor at 100 meters, and even then, not reliably. Tank for tank, the Panther was superior in every measurable category. Better armor, better gun, better optics, better crew ergonomics. German engineering at its finest, refined through 3 years of combat experience on the Eastern Front. Von Luck's 6 Panthers could theoretically destroy 30 Shermans before the Americans closed to effective range. The mathematics favored Germany. Except the Americans kept coming. 50 Shermans, then 70, then 100. Von Luck had received intelligence reports the previous week. The Americans were producing tanks at a rate Germany could not comprehend. 500 Shermans per month, 600, sometimes 700. The exact numbers varied, but the trend was unmistakable. Germany's best tank factories, working at maximum capacity, were producing 100 Panthers per month, when production was good, when rail transport delivered components on schedule, when Allied bombing didn't disrupt the supply chain, when steel allocations arrived as planned. The Americans were producing Sherman tanks faster than Germany could produce ammunition to destroy them. Von Luck knew what those numbers meant. Germany had built the finest tanks in the world. America had built enough tanks to bury Germany under steel. The question that would haunt German tank commanders for the remainder of the war was simple. How could superior engineering lose to mass production? Germany entered the war with the most sophisticated armored doctrine ever developed. Panzer divisions had revolutionized warfare in Poland and France. Guderian's breakthrough at Sedan, Rommel's advance across North Africa. German tanks were not just weapons. They were the centerpiece of an integrated combat system combining armor, infantry, artillery, and air support in coordinated maneuver warfare. The Panzer III and Panzer IV that spearheaded those early victories were good tanks, well designed for their era. They featured torsion bar suspension for smooth cross-country mobility, excellent optics for acquiring targets, reliable Maybach engines, and crews trained to exploit their capabilities. American tank design in 1941 was primitive by comparison. The M3 Lee was a stopgap design with a hull-mounted 75mm gun that required turning the entire tank to aim. The M3 Stuart light tank was adequate for reconnaissance, but useless in tank-versus-tank combat. American tank doctrine was confused, with armor advocates fighting cavalry traditionalists and infantry support specialists for resources and doctrinal priority. On paper, Germany should have maintained armored superiority for years. But paper lies. By 1943, Germany faced a fundamental problem. Every major combatant was improving tank designs continuously. The Soviet T-34 that appeared in 1941 shocked German commanders with its combination of firepower, armor, and mobility. The T-34's sloped armor and wide tracks gave it performance advantages German tanks couldn't match. Germany responded by developing better tanks. The Tiger I appeared in late 1942, mounting an 80mm gun derived from the legendary Flak 88 anti-aircraft gun. The Tiger could destroy any Allied tank at ranges exceeding 2,000 meters. Its frontal armor, 100mm thick, was effectively invulnerable to most Allied tank guns. The Panther appeared in 1943, designed to combine the T-34's mobility with German firepower and armor. The Panther mounted a 75mm KWK 42 L-70 gun, one of the finest tank guns of the war. It featured sloped armor similar to the T-34, a powerful Maybach HL-230 engine producing 690 horsepower and sophisticated torsion bar suspension. The Tiger II, or King Tiger, appeared in 1944. It mounted an even more powerful 80mm Makoke 43 L71 gun and featured frontal armor up to 185mm thick. The King Tiger was nearly invulnerable from the front and could destroy any Allied tank at extreme range. These were magnificent machines. German tank crews who transitioned from Panzer IVs to Panthers or Tigers described the experience as moving from a truck to a racing car. The optics were clearer. The gun was more accurate. The armor provided confidence that Allied shells would bounce off harmlessly. Tank for tank, vehicle for vehicle, Germany had superior designs. The problem was that Germany could not build enough of them. The Tiger I went into production in August 1942. Production continued until August 1944. Total Tigers produced 1,347 vehicles over 24 months. That represented 56 Tigers per month average production. The Panther went into production in January 1943. Production continued until April 1945. Total Panthers produced 6,000 vehicles over 28 months. That represented 214 Panthers per month average production. The Tiger II went into production in January 1944. Production continued until March 1945. Total Tiger IIs produced 489 vehicles over 14 months. That represented 35 Tiger IIs per month average production. These production numbers represented Germany working at maximum sustainable capacity. Every factory, every skilled worker, every ton of steel was dedicated to war production. Germany could not increase these numbers significantly without shutting down production of other critical weapons. The Sherman tank entered production in February 1942. The first Shermans came from Lima Locomotive Works in Ohio, a company that had never built a tank before. Lima built railroad locomotives, massive diesel-electric engines for moving freight across America. In September 1941, the United States Army approached Lima with an urgent request. Could they build tanks? Not just a few tanks, thousands of tanks, starting immediately. Lima's engineers studied the blueprints for the M4 Sherman. They saw a vehicle designed around principles they understood. The Sherman used a radial aircraft engine, the Wright R975, which was already in mass production for aircraft. The transmission was adapted from a truck design. The suspension used vertical volute springs, simple and rugged. The armor was rolled homogeneous steel, standard material available from dozens of steel mills. The Sherman was not a sophisticated design. It was a functional design optimized for mass production. Every component was chosen for availability and ease of manufacture. Where German tanks used precision-machined parts requiring skilled machinists, Shermans used cast or welded components that semi-skilled workers could produce. Lima delivered its first Sherman in April 1942, 7 months after receiving the contract. By December 1942, Lima was producing 100 Shermans per month. By mid-1943, Lima was producing 250 Shermans per month. Lima was not the only Sherman production facility. The Chrysler Corporation's Detroit Tank Arsenal, built specifically for tank production, began delivering Shermans in April 1942. The Fisher Body Division of General Motors converted automobile production lines to Sherman production. Ford built Shermans at its Grand Rapids plant. Pacific Car and Foundry in Washington built Shermans. Press Steel Car Company in Pennsylvania built Shermans. 11 major production facilities were building Shermans by late 1942. Combined monthly production reached 1,000 Shermans by early 1943. By mid-1943, American factories were producing 1,400 Shermans per month. By late 1943, production peaked at 2,000 Shermans per month. The German General Staff in Berlin received intelligence reports on American tank production and assumed the numbers were propaganda. 2,000 tanks per month was physically impossible. It violated every understanding of industrial capacity and manufacturing limitations. German tank factories required skilled workers who understood precision machining, complex assembly sequences, and quality control procedures. Training a tank factory worker took 6 months. Finding workers with the necessary skills took longer. Germany had mobilized every available skilled worker. There were no more. American tank factories hired workers off the street. Many were women. Many had never worked in manufacturing before. They were teachers, housewives, farm workers, office clerks. They learned to operate punch presses in 2 weeks, to weld armor plate in 3 weeks, to assemble transmissions in a month. The secret was the same principle Henry Kaiser had applied to shipbuilding. Break complex assemblies into simple, repetitive tasks. Design products for ease of manufacture rather than maximum performance. Accept good enough rather than insisting on perfect. The Sherman's armor was welded, not interlocked and precision-fitted like German tanks. Welding was faster. Less skilled workers could weld to acceptable standards after brief training. The welds were not as strong as German interlocked armor, but they were strong enough. The Sherman's engine was a mass-produced radial aircraft engine. It was not the ideal tank engine. Radial engines were tall, requiring a higher hull profile. They consumed more fuel than diesel engines, but radial engines were available in quantities of thousands per month from aircraft production. Installing an available engine was better than waiting months for purpose-built tank engines. The Sherman's gun, the 75mm M3, was not the most powerful tank gun available. The United States had designed a 76mm high-velocity gun that would have given Sherman's better anti-tank performance. But the 75mm was in production, available immediately, and adequate for infantry support missions. The Army chose availability over optimization. Every design decision in the Sherman prioritized production speed and volume over maximum performance. The result was a tank that was adequate rather than excellent, but available in overwhelming numbers. By the time the first Panthers rolled off German production lines in January 1943, America had already produced more than 10,000 Shermans. Germany would produce 6,000 Panthers over the entire war. America produced 50,000 Shermans. The ratio was not quite 10-1. It was worse than that. A Panther required approximately 150,000 man-hours to build. A Sherman required 10,000 man-hours to build. Germany was using 15 times more labor to produce each tank than America, and America was still outproducing Germany by factors of 5 or 6-1. The mathematics were devastating. For every hour Germany spent building one Panther, America could build 75 Shermans. The actual production ratios were limited only by steel availability and factory capacity, not by labor or complexity. German commanders in Normandy after D-Day experienced this disparity firsthand. A panzer division defending against the Allied breakout might destroy 5 Shermans for every German tank lost. The kill ratios favored Germany significantly. But 5 destroyed Shermans were replaced within a week. 1 destroyed Panther took 3 months to replace, if it could be replaced at all. SS Obersturmbannführer Michael Wittmann, one of Germany's most successful tank commanders, destroyed 138 Allied tanks during his career. His Tiger I could engage Shermans from distances where return fire was impossible. At the Battle of Villers-Bocage on June 13, 1944, Wittmann's single Tiger destroyed approximately 25 British tanks and armored vehicles in 15 minutes. This was the tactical advantage German tanks possessed. Superior firepower, superior armor, superior optics allowing German crews to engage Allied tanks before Allied tanks could effectively return fire. In any individual tank versus tank engagement, German tanks had overwhelming advantages. Wittmann was killed on August 8, 1944, when his Tiger was destroyed by Allied tanks near Caen. His tank was replaced by nothing. Germany had no replacement Tigers available. The factory producing Tigers had been bombed. component deliveries were disrupted. Skilled workers were being drafted into the Wehrmacht as Germany faced manpower shortages on all fronts. The Sherman that destroyed Whitman's Tiger was replaced 3 days later. Another Sherman rolled off the production line in Detroit, was loaded onto a ship in New York, crossed the Atlantic, was unloaded in Cherbourg, and drove to the front line. Total time from factory to combat, 6 weeks. The industrial disparity extended to every aspect of tank warfare. German tanks required specialized tools for maintenance. Panther transmissions required specially trained mechanics using specific hydraulic equipment to remove and replace. If a Panther's transmission failed in combat, the tank was immobilized until a maintenance unit with the correct equipment could reach it. Sherman transmissions could be removed with basic tools by any mechanic with truck maintenance experience. If a Sherman's transmission failed, the crew could often replace it in the field using spare transmissions carried by supply units. If the tank could not be repaired immediately, it was abandoned and replaced. The crew walked back to supply depots, received a new Sherman, and returned to combat. Germany could not afford to abandon tanks. Every Panther represented months of production time, tons of scarce steel, and irreplaceable skilled labor. German recovery units would risk crews and equipment to recover disabled tanks from the battlefield, often under fire, because losing a tank permanently was a strategic catastrophe. America could afford to abandon damaged tanks. If a Sherman took a track hit in an exposed position, the crew bailed out and left the tank. Recovery was attempted, if convenient, but if not, the tank was written off. Another Sherman was already on its way from the port. This difference in replacement capability shaped tactical doctrine. German tank commanders were cautious. They planned attacks carefully, used terrain to minimize exposure, and avoided unnecessary risks. Losing a tank meant losing irreplaceable combat power. American tank commanders were aggressive. They attacked prepared positions, accepted losses, and pushed forward knowing that destroyed tanks would be replaced quickly. The tactical calculus favored aggression when replacement was guaranteed. The Battle of Aricourt in September 1944 demonstrated these dynamics clearly. The 4th Armored Division, equipped with Shermans, engaged elements of the 5th Panzer Army equipped with Panthers and Panzerdiefus. The Germans had terrain advantages, firing from prepared positions with clear fields of fire. The 4th Armored Division lost approximately 40 Shermans in the first day of combat. The Germans lost 14 tanks. The kill ratio favored Germany 3-1. By the 3rd day, the 4th Armored Division had received replacement Shermans from supply depots. The German panzer units had received no replacements. Their 14 destroyed tanks were irreplaceable losses. The battle continued for 2 weeks. The 4th Armored Division lost approximately 100 Shermans total. The Germans lost approximately 100 tanks, including Panthers, Panzerfes, and assault guns. The kill ratios were approximately even, but the strategic outcome favored America overwhelmingly. The 4th Armored Division ended the battle at full strength. Replacement Shermans arrived continuously from supply depots. The German panzer units ended the battle at 40% strength. No replacements arrived. Those units would not return to full combat effectiveness for months, if ever. This pattern repeated across every front where American and German armor clashed. Germany won tactical victories through superior tank design and crew training. America won strategic victories through industrial production and logistics. The German economy could not support continuous tank production at the rates required. Building Panthers required specialized steel alloys for armor and gun tubes. Germany produced adequate steel, but refining that steel into armor-grade plate required specialized facilities, additional processing, and scarce alloying elements like nickel and molybdenum. American steel production in 1943 exceeded 80 million tons. German steel production in 1943 reached 34 million tons. America was producing more than twice as much raw steel as Germany, but the gap was wider when accounting for armor-grade steel. American steel mills could allocate huge quantities to armor plate without impacting other war production. German steel mills rationed armor plate carefully across competing demands. Sherman armor was relatively simple, rolled homogeneous steel. It was not the hardest possible armor, but it was adequate for the Sherman's role and could be produced in vast quantities. Panther armor used sophisticated face-hardened steel that required additional heat treatment and processing. It was superior armor, but production was limited by manufacturing capacity. Every Panther required approximately 15 tons of finished armor plate. Germany's armor plate production in 1944 averaged approximately 30,000 tons per month. That would theoretically support production of 2,000 Panthers per month, except that armor plate was also required for Tiger tanks, assault guns, tank destroyers, and armored vehicles of all types. The German Army operated dozens of different armored vehicle types simultaneously. Panthers, Tigers, Tiger the Steckus, Panzerfus, Panzer IIIs, Stu G3 assault guns, Hetzer tank destroyers, Jagdpanther tank destroyers, Jagdtiger heavy tank destroyers, and numerous specialized variants. Each type required different components, different spare parts, different maintenance procedures, and different crew training. This diversity emerged from German engineering culture. When German engineers identified a requirement, they designed the optimal solution for that specific requirement. Need a heavy tank? Design the Tiger. Need a tank destroyer? Design the Jagdpanther. Need a light assault gun? Design the Hetzer. Each vehicle was optimized for its mission. The result was dozens of excellent vehicles, none produced in sufficient quantity. Spare parts became a nightmare. A Panther's road wheel would not fit a Tiger. A Panzer IV's engine would not fit a Panther. Every vehicle type required unique spare parts, unique tools, and mechanics trained on that specific vehicle. American armor doctrine followed a different philosophy. Design one good tank. Produce it in overwhelming quantity. Train everyone on the same vehicle. Stockpile parts for that vehicle. The Sherman was not the best tank for every mission, but it was adequate for most missions, and it was available everywhere in enormous numbers. American armored divisions fielded almost exclusively Shermans. Tank battalions had Shermans. Tank destroyer battalions had Shermans mounting 76mm guns or 3-inch guns. Armored reconnaissance had Stuart light tanks, but Stuarts used many Sherman components. When mechanics needed spare parts, they knew what parts to stock. When crews needed training, they trained on Shermans. Germany discovered too late that this standardization provided overwhelming logistical advantages. When Panther battalions advanced into the Soviet Union, they carried trucks loaded with spare parts specific to Panthers. When those spare parts were exhausted, which happened regularly during extended operations, the Panthers could not be repaired. Disabled Panthers were abandoned because the parts needed to fix them were 500 kilometers away at the nearest supply depot. When Sherman battalions advanced across France, they carried spare parts that fit Shermans. Every supply truck carried Sherman parts. Every maintenance unit had Sherman parts. Every port stockpiled Sherman parts. When a Sherman broke down, parts were available immediately. The Sherman's engine, the Wright R975, was a radial aircraft engine used in hundreds of aircraft types. Spare engines were available at every airfield, every supply depot, every port. If a Sherman needed an engine replacement, the crew could sometimes scavenge an engine from a damaged aircraft. The logistical flexibility of using common components across multiple vehicle types gave American forces enormous advantages. German tanks used purpose-built engines that fit only that specific tank type. A Panther's Maybach HL-230 engine would not fit any other vehicle. If a Panther needed an engine replacement, the crew waited for a new Maybach HL-230 to arrive from Germany. That could take weeks or months, depending on transport availability. By late 1944, Germany faced cascading production failures. Allied bombing had destroyed or damaged many component factories. The Maybach engine plant in Friedrichshafen was bombed repeatedly. Production dropped from 400 engines per month to 150 engines per month. That immediately limited Panther production because assembling a Panther without an engine was pointless. American tank production faced no such bottlenecks. The Wright R975 engine was produced by multiple manufacturers at facilities spread across the United States. If one factory had production problems, other factories increased output to compensate. The decentralized production system was inefficient in peacetime but remarkably resilient in wartime. The final blow to German tank production came from raw material shortages. Building tanks requires steel, obviously, but also copper for electrical systems, rubber for road wheels and tracks, petroleum products for lubricants and fuels, and rare alloying elements for specialized steel. Germany obtained copper from mines in occupied territories and from recycling programs that stripped copper from civilian infrastructure. Church bells were melted down for copper. Electrical wiring was removed from civilian buildings. Copper plumbing was replaced with iron pipe. These measures provided some copper, but never enough. American copper production in 1943 exceeded 1 million tons. German copper production in 1943, including all occupied territories and recycling programs, reached approximately 200,000 tons. America had 5 times more copper available for tank production, and copper was just one of dozens of critical materials where America had overwhelming advantages. Rubber presented even worse problems for Germany. Natural rubber came from Southeast Asian plantations, which Japan controlled but could not effectively transport to Germany due to Allied naval dominance. Germany developed synthetic rubber, but synthetic rubber production required petroleum feedstocks and complex chemical processes. Germany's synthetic rubber production never exceeded 100,000 tons annually. American rubber consumption in 1943 exceeded 800,000 tons. The United States imported natural rubber from South America and produced synthetic rubber domestically. Sherman tanks used rubber road wheels, rubber track pads, and rubber components throughout the vehicle. Rubber was abundant enough to be considered expendable. German tanks increasingly used steel road wheels to conserve rubber. Steel wheels worked but increased ground pressure, reduced cross-country mobility, and created more track wear. Panthers late in the war used all steel wheels, sacrificing performance to conserve rubber. These compromises accumulated. A Panther. Built in 1943 with rubber road wheels, full armor protection, and quality components, was an excellent tank. A Panther built in late 1944 with steel road wheels, simplified components, and substitute materials was still a dangerous opponent, but noticeably inferior. Sherman quality remained consistent throughout the war. A Sherman built in late 1944 was essentially identical to a Sherman built in 1942, sometimes better because manufacturing refinements improved durability and reduced production costs. American industry could maintain quality because raw materials remained abundant. The crew experience differential compounded the equipment differential. German tank crews in 1944 were increasingly inexperienced. Veteran crews were being killed faster than training schools could replace them. Panther drivers received 6 weeks of training instead of the 16 weeks required in 1943. They could operate the tank but lacked the experience to handle difficult terrain or mechanical problems. American tank crews received extensive training in the United States before deployment. Training facilities had hundreds of Shermans available for instruction. Crews spent months training on the exact vehicle they would operate in combat, learning its capabilities and limitations thoroughly. More critically, American crews knew their tanks would be replaced if destroyed. German crews knew their tanks were irreplaceable. That psychological difference affected tactical decision-making. American crews took risks, knowing that tank losses were acceptable. German crews hesitated, knowing that losing their tank eliminated their combat effectiveness permanently. The final Sherman production numbers were staggering. The United States produced 49,234 Sherman tanks in all variants from February 1942 through July 1945. 49,000 tanks in 41 months. That represented 1,200 tanks per month average production, though monthly production peaked much higher at certain periods. Germany produced approximately 24,000 tanks of all types from 1942 through 1945, including Panzer IIIs, Panzer IVs, Panthers, Tigers, and Tiger IIs. That represented 500 tanks per month average production. America outproduced Germany 2.4 to 1 in raw numbers, but the gap was wider when accounting for production efficiency. Germany used 10 times more industrial capacity per tank produced than America. German tanks required more steel, more labor, more machining time, more specialized components. If production efficiency is factored into the comparison, American effective tank production was 20 times greater than German production. By early 1945, German panzer divisions existed on paper but had no tanks. Training units in Germany had no training vehicles. Replacement tanks were not arriving at the front. Crews were being trained on obsolete Panzer IIIs because no modern tanks were available for instruction. American armored divisions in early 1945 were operating at 120% of authorized strength. More Shermans were arriving than could be absorbed by existing units. Tank battalions had spare Shermans parked at supply depots, waiting to replace combat losses that might occur tomorrow or next week. The Battle of the Bulge in December 1944 demonstrated the final consequences of this industrial disparity. Germany assembled its last strategic reserve for one final offensive in the Ardennes. The offensive committed approximately 1,400 tanks and assault guns, including nearly 500 Panthers and Tiger IIs. It was Germany's largest armored force assembled since 1943. The attack achieved surprise and initial success. German forces penetrated Allied lines and created a dangerous salient. American forces were pushed back, took heavy losses, and appeared to be collapsing. Then American logistics took over. Within 5 days, more than 200 replacement Sherman tanks arrived at the front. Within 2 weeks, 500 replacement tanks arrived. Within a month, every Sherman lost in the initial German assault had been replaced, and American armored strength exceeded pre-battle levels. German tank losses during the Battle of the Bulge exceeded 600 vehicles. Those losses were never replaced. The panzer divisions that fought in the Ardennes ceased to exist as effective combat formations after the battle. They would not fight again as armored units. By March 1945, Germany had fewer than 1,000 operational tanks on all fronts combined. America had more than 15,000 Shermans in Europe alone, with thousands more in the Pacific, thousands more in training centers in the United States, and hundreds more rolling off production lines weekly. The war ended in May 1945. Germany's tank production facilities were destroyed or captured. The remaining Panthers and Tigers were abandoned for lack of fuel. The United States had enough Sherman production capacity that factories were closing voluntarily because the military had more tanks than it could possibly use. The title says Germany built the best tanks. That statement is accurate. The Panther was superior to the Sherman in nearly every measurable performance category. German engineering produced remarkable machines. But the title also says America built 50,000 Shermans and won anyway. That statement captures the essential truth about industrial warfare. Superior engineering matters in peacetime competition and small-scale conflicts. In total war between major industrial powers, production capacity determines outcomes. Germany built 6,000 Panthers over 2 years and lost the war. America built 50,000 Shermans over 3 years and crushed Germany under an avalanche of adequate equipment delivered in overwhelming quantity. The lessons remain relevant today. Wars between industrial powers are won in factories years before the first shot is fired. Designing perfect weapons is less important than designing weapons that can be produced in sufficient quantity to sustain combat operations. Logistics and industrial capacity matter more than tactical excellence or individual equipment superiority. German tank commanders understood this too late. Hans von Luck, watching those 50 Shermans crest the hill near Mortain, knew his 6 Panthers could destroy perhaps 20 of them before being overwhelmed. The mathematics were clear. 20 destroyed Shermans would be replaced within a week. 6 destroyed Panthers would never be replaced. The war was decided not by which tank was better, but by which nation could produce more tanks. America won because American factories could build Shermans faster than German guns could destroy them. That simple fact, more than any battle or any commander's brilliance, determined the outcome of the war in Europe.